How are you?
Doing well. How about you guys?
Yeah.
It's
Yeah,
too
we're
bad.
doing
Too bad I'm missing most of the conference because
time zone is different.
yes.
So are you going to talk about the new results?
It's going to be mostly a review, but there are some small new reinterpretations. Like the new results are reinterpretations of old things.
Yeah, this is a very interesting topic. Yeah, final state. Yeah, it's problem.
The audience looked very broad, so I thought I should.
Yeah. Quantum information, condensed matter, cosmology, and string theory.
Yes.
Yeah, it's great. Yeah, if you have a kind of introduction.
Yeah, it's going to be mostly review, so we'll see.
Andrew is chair.
Wait, hello.
Well,
You were also before in Yukawa Institute.
so can I say it again?
Yeah, several years ago you visited us, right?
Yeah, that's right. Yeah. Yeah,
unfortunately, this time we cannot have an actual conference.
Yeah. Hopefully soon things will change.
Yeah.
How easy is it to get a vaccine in Japan?
It's just started, so only medical people.
Okay.
It's very small fraction. I think US is more advanced.
Mm-hmm.
Yeah, few minutes. Yeah, people are just joining just on time, so it's good to wait 1 minute or 2 minutes.
That's fine. That's fine. How are you guys doing questions? Just at the end or also in the middle of the talk?
Yeah. What is your preference?
To interrupt me anytime. I'm being interrupted for questions. I'll make that clear at the beginning of my talk. I'll mention it.
Yeah.
Is the connection fine, by the way, or?
Yeah, I think so.
Yeah, I can hear you at least. Yeah. So I think maybe we can start.
Yeah. I think we could.
Okay. So our second and last speaker this session is Ahmed Almheiri from the Institute for Advanced Study, and he'll be telling us about comments on the final state proposal and the gravitational path integral. So whenever you're ready, please take it away.
Okay, thanks a lot. So thanks for the invitation to speak at this one conference. It's unfortunate that I'm asleep for most of it, but hopefully I'll watch the recordings. So I'm gonna make some comments about, comments and make some connections between this old idea of the final state proposal, where to address the information paradox, you have to put a final state at the singularity, and which is due to Juan Maldacena and Gary Horowitz, and to connect it with the more recent results on the gravitational path integral and what that taught us about the black holes and quantum information. Please interrupt me at any point during the talk for questions. I'll try to go slow, and yeah, so questions are very welcome. So what I'm going to talk about today is based. It's already a lot of it is present in many papers, featuring and also a talk by Douglas Stanford at KITP, and also a lot of the diagrams are going to be similar to those that appear in papers by Marolf and Maxfield. The comments I'm going to say at the very end will be sort of a new interpretation of old results. Okay. Let's see. All right, so the outline of my talk is going to be the following. I'm going to recap the information paradox very quickly. I will then review the final state proposal, discussing both its strengths and limitations. After that, I'll derive some lessons from the gravity path integral and finally address the limitations of the final state proposal from those lessons. Okay, so the information paradox. So everyone is familiar with this, but let me go through it to set the conventions. So suppose you have a black hole formed from collapse of some star or matter, which I'm calling M, in some state I. By the way, can you guys see my cursor?
Yes, we can see it.
Okay. The black hole this black hole will evaporate away by a pair creation at the horizon. I will represent all of the Hawking radiation abstractly by these two lines, where R is the outgoing Hawking radiation and R tilde is the interior set of partners to R. And as Hawking taught us, the state of the Hawking radiation, it's not too far from something like this, which is a maximally entangled state of a pair of d-dimensional Hilbert spaces representing R tilde and R. Here, D, you should think of it as e to the s Bekenstein-Hawking entropy of the black hole. Now, the problem here is that if you look at the state at late times, the total state on a Cauchy slice that covers both the interior and the exterior of the black hole, here I'm writing it as psi, is simply the product of the state I of the matter and the entangled state of all of the Hawking radiation and their interior partners. If you imagine that this state defines an evolution, or rather, if you imagine that the evolution of this black hole evaporation process is to go from M to R, or said differently, for an outside observer, it looks like the state M went to this, the state of M went to the state of R, and you can show from the state simply by tracing out M and R tilde that the density matrix of R is proportional to the identity matrix times some normalization 1 over D. And so the evolution is not unitary. You went from a pure state of the matter to a mixed state of the radiation. You can check that by computing the purity, for example, which is like trace of rho squared, and it's equal to 1 over D times the trace of rho, and therefore it's not equal to 1, and this is a check that you have a mixed state. The problem, as we know, is that everything, all the information about, essentially what's happening is that everything is getting stuck at the singularity. And what we need to do is we need to move things from the singularity to the outside. That's where the final state proposal comes in. The idea is that you can move things from the singularity to the outside by using post-selection, okay? And the philosophy here, by post-selection here, I mean you impose some final state on the singularity. The philosophy the motivation for this is well, one motivation is that we know that in the Big Bang, you have a space-like singularity at the beginning of the universe. We imagine that starts in some initial state. Well, why not future singularities too? Why can't future singularities also have a final state? This is sort of one way to think about this. And the idea here is that so while the Big Bang singularity would be a ket, a final singularity should be a bra. And what it would do is that it would project on the combination of the matter and the interior Hawking modes. The final state here is the following bra vector on M and R tilde. And it's what it does is that it projects M and R tilde onto a maximally entangled state between the two. Note that the state F is not normalized, and I'll say why that's the case in a second. You have to multiply by D the dimension of the dimension of, say, the interior modes, times some unitary matrix S over here. Okay, we can choose this S to be whatever we want. And now the rules for computing what the resulting state is of the radiation is to simply project the state F on the combined state psi of M, R tilde, and R. If you do that and run through the algebra, you'll just get this state. So you'll get a pure state of the system R. And so the evolution from the outside looks like it went from an initial state I to the state SKI on K. So this is just S on I roughly, basically. So you can think of this S as the S matrix of the black hole. Now the reason why this D was inserted is so that this new state has unit norm. Okay, that's why you need to unnormalize the final state projection. actually, yeah, one way to, so one, just intuitively, the reason why this had to have a large normalization is because you're doing a measurement, and it's only with probability 1/d that you'd get the result that you wanted, and so you need to rescale things. That's another way of thinking about it. Okay, so this is how the final state gives us unitary evolution. So that's great. One more thing is that this process can be represented by this quantum circuit. So basically, the matter comes in, and also an R tilde, and then you get this projection on M and R tilde. And what this does is that it provides a path for the information I to make it to the outside. Okay, this is a symbolic representation of the equations on the previous slide. Okay, so this is good. We get unitary evaporation. However, it turns out that there are many issues with this proposal. I'm only going to discuss one of them that was pointed out by Raphael Bousseau and Douglas Stanford. Before I do that, let me first modify the setup slightly. Instead of starting with a pure state of the matter, I'm going to consider a situation where the black hole is fully entangled with some external system or some reference. And I'm going to represent that using this diagram here. So this is something you can imagine preparing such a black hole by collapsing matter that's maximally entangled with something else. Moreover, what I'm going to do is that I'm going to decompose the state into two sets of maximally entangled subfactors. One with dimension 2, that's B tilde and B, and R tilde and R have some large dimension D. Okay, roughly speaking, what I'm doing is that I'm separating the Hawking radiation into, I'm isolating one pair of modes from the rest of the radiation. Okay? You'll see why I'm doing this in a second. The final state that you need to apply in this case is slightly different from the one that we did in the previous slide. The condition on the final state is that the state B tilde, the state of B tilde in this final state is maximally mixed. So differently, if you were to compute the density matrix of B tilde starting from this final state F, that's represented by this quantum circuit where you're tracing out the R tilde, you should get something which is proportional to the identity. And again, it's proportional to the identity with some weird normalization, basically because of the same reason that I mentioned before. Okay, you can check that this normalization is the right one for the resulting state after you project to give you to be unit normalized. Anyways, after you project on the state psi, so psi is again it's the global state of B tilde and B entangled and R tilde and R entangled. And if you project on the state with the state F, you get the following. It's represented by the following quantum circuit, and it's clear here that the state is going to be pure of B and R, the state outside. Here's just a quick comment. I'm not sure if this is going to be useful. This condition on the density matrix of F is what ensures that there's an isometry from B tilde into R. Okay, that's just our comment. Any questions up to this point? Okay, very good.
Actually, I didn't understand your picture because you look like like the black hole is entangled with B and R, but you said you created one that was entangled with a reference.
Oh, what I meant by the reference was R, or you should think of the reference as being the union of BR.
Okay.
So you have a black hole with matter as entangled with the reference being the union of BR. You can think of it like that.
But all right, fine. But this is almost the same picture you had before. You have a black hole plus its radiation in the total pure state.
Exactly.
Okay.
So the only difference is that I don't have the matter falling in.
Okay, but the setup was such that your hypothesis led to the same picture that you have here, actually, I think.
Yes. That's right. The words I'm going to okay. The way I'm going to describe this black hole now is that I'm going to say that, well, I'm going to describe these lines as saying that these are modes of Hawking radiation. Okay? Even though I use the word reference and so on, but for now, let me stick to the following convention. I'm going to say that all I'm drawing here are just Hawking radiation. I'm going, and here we just have the Hawking state between interior Hawking modes and exterior Hawking modes, and I've isolated a pair of modes. Is that okay? Okay. Now let's, so what Bousseau and Stanford point out is that if you do, the measurements or the amps measurements, you find interesting and weird results. So the final state got a second life during the firewall era because it seemed to give you exactly what you wanted: a smooth horizon and purity for the outside. Let me describe that. So let's imagine that you perform the following experiments on the black hole. So here, let's imagine you do a measurement on B tilde and B to check whether they're maximally entangled or not. So this measurement checks whether you have a smooth horizon or not. Also, consider the following measurement that simply checks that B and R are in this pure state that you've prepared them in. Okay, that's represented by this projector. Okay, I'm going to go back a slide. So this is what the state is of B and R. And so what the projector does is that it simply checks that B and R are indeed in that prepared state. Okay, so this checks that B and R are in some pure state. Now, the thing that we're going to be computing is the probability for the success of these measurements. The way you do that is you consider here on the right-hand side, the probability can be written as these two factors. This on the right-hand side, this is the ket having done some projection and then acted with the final state. And here on the left factor is the bra having done a projection and then projected with the final state. This thing defines the probability of this measurement. This follows just from the usual formula for how to compute probability. Usually you start with a density matrix, you dress it with projectors, and then you take the trace. That defines the probability. But now we have a final state, so you need to stick in a final state density matrix at the end. Okay, that's a proposal for how to compute probabilities in the presence of a final state. Okay, now let's actually compute these probabilities for these two measurements. So the first calculation here checks that B tilde and B are indeed entangled. Okay, so this is a quantum circuit computing the probability. Let's go through it from the bottom to the top. So you start here with the entangled state of R tilde B tilde with B and R. Then at some point here, you do the measurement pi B tilde B. Okay, so this checks that B tilde and B are entangled. And then you project to the final state. Okay, so this bottom half of the picture is the ket, and the top half is identical. It's just a mirror image. It's the bra. And then to compute, well, then you can put some numbers to this. You can show, well, here, this 1 over square root of 2D is the normalization of the initial state. The 1 over 2 comes from the definition of the projector. this 2D here comes from this condition that we had on what the on the final state, giving a mixed being proportional to the identity for B tilde, for the density matrix of B tilde. And so, and you multiply all these numbers together, you take into account that you get a factor of 2 from these loops, and you get 1. Okay, so there's a very simple calculation showing that indeed the probability of finding a smooth horizon in this projected state is 1. Very good. Oops. Next, we can, let's talk about just checking that B and R are indeed in the right entangled state. Well, you insert these projectors, that's the highlighted pieces. Again, you find, basically you find three factors of the inner product of the state. And given the normalizations and everything, I promise you that this is also equal to 1. Okay. I'll give you guys just a few seconds to see, for whoever wants to do the multiplication in their heads. Basically, there are 3 loops here, and each loop gives you a factor of 2D, and then that cancels with all of the normalizations. Okay, so that's good. So again, it seemed like we have a smooth horizon and we have unitarity. So this was good, except something funny happens, again pointed out by Douglas and Raphael, when you try to compute the probability of first finding that B and R are in, sorry, I'm trying to move something, that B and R are in the pure state, and then that B tilde and B are maximally entangled. So the picture is the following. So you start with the entangled state, you do the BR measurement that checks that it's in the state that you prepared it in, and then you do the measurement on B tilde and B. Okay, and then you project on with the final state, and similarly for the bra. And in this case, the thing that happens, what this measurement does is that so without this measurement, this circuit factorizes into a product of 3 loops, but these measurements connect up the loops into one big loop. So you lose some factors basically. And so again, you have the normalization of the state, you have the normalization of the operators, you have one big loop, which gives you a factor of 2 times d to the 3, which again follows from the condition on the final state. And you multiply everything together and you get 1 over 2 to the 4, which is not equal to 1. So what's going on? So it was very promising at the beginning that this would resolve, the firewall paradox. But if you try to do the AMPS experiment for an infalling observer, you find that you find something weird. Basically, here's a quick summary. Even though the probability is 1 for individual measurements, the probability of the 2 measurements is less than 1. So this introduces acausality, right? It tells you that the statistics of doing the outside measurement depends on whether a future measurement is going to take place. And the thing that I'm going to talk about next for the rest of the talk.
Excuse me,
is
sorry,
how
in this statement, pi BR is the outside measurement, and
yes,
pi B tilde is the future measurement.
Exactly, yes. From the perspective of an infalling observer, they would first do the BR measurement, and then the future measurement would be the one they would do when they pass through the horizon and check the B tilde B measurement. Entanglement. Okay. The goal for the rest of the talk is to address this problem using intuition from the gravitational path integral. But just before I talk about that, let me note something interesting. So let's consider what happens when you act on the state psi just with the outside measurement, okay, the BR measurement. And also we can project with the final state. Remember that all this measurement does is that it simply checks that the state is indeed in the state that you thought it was in, that it's in the state psi projected on by F. So it can be written like this. There's a normalization which I'm ignoring. And here is the corresponding circuit representation for this calculation. I've written this in a suggestive way, just to point out that there are actually two final states when you consider the state acted on with pi br. And correspondingly, there are two interiors, which I'm calling R tilde B tilde and R tilde prime B tilde prime. And so there's sort of the question of which of these two interiors / final states are the quote unquote real ones. And what we'll see is that in some sense, it's R tilde B tilde that becomes the real interior, and this is going to be motivated by analyzing the gravitational path integral, and in particular, and the punchline is going to be is that in this final state discussion so far, we have not taken into account that the interior is secretly part of the exterior. B tilde is secretly part of R. Okay? And that's going to be the crucial new ingredient. Is there a question?
When you say secretly, I mean, I guess when you're teleporting the state outside by this final state thing, there's like a closed time-like curve in some ways. So it's a bit confusing as to when you're drawing these diagrams, what you mean by the past and the future, because as soon as I interact, I mean, you have information coming out superluminally for all intents and purposes. So I guess it's a bit confusing what you mean by the past or the future, because once you make these things interact, there's a closed time-like curve, right? So how do you get it?
I think so. Good. Yeah, you're saying in some sense, B tilde is to the past of R. So if I do a measurement on R before I do a measurement on B tilde, it seems like I'm going backwards in time.
Yeah, I can see that the one state is the future of the other state, and so when they interact, then it's like its past self is interacting with its future self.
I think that's basically the issue. Like the new proposal, if you let me come back to this point later. I think I think that is really the crux of the issue. Okay. Somebody should get muted, I guess. Okay. Okay, so now let's talk about the gravitational path integral. Okay? I'm going to consider a simple model to demonstrate some of the physics I want. And I'm going to consider this model of having let me start again. So I'm going to discuss how the gravitational path integral gives a vanishing entropy for the radiation, and also how it grants access to the interior from the radiation. And I'm going to do this using a model involving closed universes. So let's consider a set of closed universes represented here that are prepared via some Euclidean evolution. So here you can imagine, here I have a Euclidean ADS. You can think of this as just JT gravity, Euclidean JT gravity. And I'm generating a spacetime by starting from some asymptotic boundary and doing some Euclidean evolution. I've also inserted these end of the world branes. Basically, this is what guarantees that I have a cosmology when I continue to Lorentzian time. The details are not important, but here's an aside on that comment. If you continue this space-time to Lorentzian time, the two end of the world branes crunch. They just collapse into one another. Okay, so here the interpretation is that this is some closed universe, and it's in some state psi IA. CU stands for closed universe. IA represents some operator insertions that I can choose to insert at some points on the Euclidean, past Euclidean boundary. Okay, so this is some basis of states for the closed universe. Now what I'm going to do is I'm going to entangle these closed universe states with some reference system R, or radiation, or call it whatever you want. And the state is going to look something like this. Here it's I'll explain the normalizations on the next slide, but D here is the number of, or the normalization that the normalizations are going to be more clear on the next slide. The D here is just the rank of the index I. Z is going to be the partition, the disk partition function of JT gravity, say. The point here is that this is sort of a model for the sort of all of the Hawking radiation entangled with everything inside of a completely evaporated black hole. Okay, and let me go back. Even though this state looks like it's a mixed state of R, now let's discuss how the gravitational path integral actually implies that the state of R is pure. And you can check that by direct computation. So as a warm-up, let's just compute the trace of rho R. So what you do is you take 2 copies of the system, and then you trace over the system R. And then you run the machinery of the gravitational path integral. What that does is that, or that means is that it says you need to consider all gravitational solutions with these 2 boundaries as their asymptotic boundary. And in this case, it's very simple. It's just this quote unquote disk, or this disk where you sort of, the branes sort of bite out a small portion of them. From the disk, you get a factor of Z, and from the index I contraction, you get a factor of D. And so with this normalization, you get 1. Hooray. So trace rho is equal to 1. That's fine. Now let's compute the purity, trace rho squared. So this is the thing that would diagnose whether the state is mixed or not. And so you take 2 copies of the system and you contract things in the right way, consistent with this matrix multiplication and the trace. Then you run the gravitational path integral, and you consider all possible connections between these asymptotic regions. And you find that to leading order in 1 over D, this piece is what wins. Okay, it's a factorized piece where each it's a factorized piece, each of which gives you a factor of trace rho essentially. And so this thing inside the square bracket is simply 1 because of the previous calculation. And so we get 1 plus factors of 1 over D. Okay, so to leading order in D, we also have a pure state. Okay, I'm not gonna, so these corrections are a small deficiency of the model, and I'm not going to make any comment on them. So the gravitational path integral doesn't quite give you unitary answers. There's a small non-perturbatively small non-unitary contribution, but I'm not going to discuss that. Anyways, I'm just going to say that to leading order, R is pure. Next, let's see how the interior is part of R. Basically, just the idea that you can act on R and affect the state of the matter inside the closed universe. So this was discussed in this paper of Pennington et al. West Coast model, they consider something called a PETS map. In our case, this operator, which accesses the closed universe, can be written as just this O and R BA, which is the operator that takes the closed universe in the state A to the closed universe in the state B. So A and B, it was A is the state of this additional particle falling into the closed universe. And to check this, what you need to do is you start with the state psi A, you act on it with OBA, and then you just check that the overlap of this state with the closed universe state in the state B is equal to 1. Well, here's the check. It's pretty simple. The blue here is the psi A, the cat. The orange is psi B, the bra, and the purple is the operator. And if you run the gravitational path integral machinery, well, this is identical to the purity calculation that we did before. Okay, so again, you get 1 plus corrections. Very good. Now, the important point is that effectively what's happening is the following. When you acted on the state psi with OBA, the operator O, what happens is that the old sort of closed universe gets contracted with or gets projected out using the bra of the operator. And all that remains, the new universe that you've created is simply the ket of the operator. That's this upper part here. Okay, so the action of this special operator R, the way that it creates the closed universe in the state B from the closed universe in the state A is that it projects out the universe in the state A and it creates a new universe in the state B. So that's how it works. And well, any questions about this model? Okay, let me give another, there's a question.
Is this what I can think of as the inside being teleported outside, so that the universe is destroyed, and there's this notion that it kind of crosses, effectively is the same system that just has crossed the horizon, and the new system is the future of the old system. Is this the equivalent description?
I'm not sure, because here I'm saying you literally get rid of the old black hole or the old closed universe and you create a new one. Your comment.
But it's in the same state as the old. It's in the same state as the old one.
No, it's a new state, right? So the old black hole was in the state A. Well, then in this case, it's the closed universe. It was in the state A. But after the action of the operator, you get rid of the old universe and you create a new one in the state B. Okay. Another very quick example of the same procedure or the same physics, but in a more realistic model, is suppose we start with some black hole where if you consider some region R far away from the black hole, let's suppose that it has a quantum extremal surface, which I'm sure you guys have heard a lot about those in this conference, and therefore it has some island I. The operator which takes this black hole, which has the state A in the island to some state B in the island, looks something like this. Okay, so this is schematic. Here, the way that the operator is defined is that it acts on the region R, and that's what I mean by this I and J here. So this will become clearer in a second. And the ket of this operator involves a particle B coming in, while the bra has a particle A coming, so going backwards in time. And this will hopefully become clear in the next slide. The action of the operator on the state is the following. So first, let's just focus on this pink and this pink region here. So this pink region, it gets contracted with the pink region of the Cauchy slice that I was considering before. So let me go back. So here there's a Cauchy slice, sigma. That I'm representing the original space-time, the state psi, only up to that Cauchy slice. When O acts on the state, the pink region gets contracted with R. Now, because of this contraction, as you guys might have heard from the previous talks, is that what this contraction does is that it creates a wormhole between the operator O and the interior of the black hole. That's the thing that gives that's the thing that sources the island. So automatically the gravitational path integral contracts the green region with the green region here, with the island region. And so everything that got contracted now just disappears. And you have a new space-time, which is composed of the old blue region, which was not affected. This was the region that was there in the original space-time, plus a new gray region, which was created by the operator, and a new orange region, also created by the operator. So the operator had a particle B going in the orange region, and therefore the new space-time will have a particle B in the orange region. So again, similar to the closed universe example, what this operator does is that the interior island gets replaced by a new interior from the operator. Okay. So now we can go back to the final state. So this is the thing that I discussed just before the gravity path integral discussion. So when you consider the state psi acted on with a projector pi br, it looks like you have two final states with two interiors, the r tilde b tilde and r tilde prime b tilde prime. The discussion that we just talked about tells you that in order to compute that, let me see, that what you should interpret as the new well, in the gravity path integral, acting on the region R tells you that it's the new interior, or rather it's the interior that is part of the operator on R that should be thought of as the physical new interior. And so this means that if you then decide to do the smooth horizon measurement, which is to measure b tilde prime b, sorry, there was supposed to be a tilde here, it disappeared. If you choose to do this measurement, you should do it on b prime b, okay, or b tilde prime b. So the smooth horizon measurement should be inserted here. It should be inserted in the ket of the pi br measurement, as opposed to what Bousseau and Stanford did, which is to put the measurement to contract b with the old b tilde. Right. This is sort of what I interpreted. It's sort of this quote unquote flaw is how I interpreted Jonathan's comments, that the reason why this thing gives you a weird answer is because you're doing a measurement on something which is in the far past, like b tilde after it gets projected, you should think of it as now it's part of the past. And the reason why you get a funny answer in the Bousseau-Stanford protocol is because you're going backwards in time and accessing the old b tilde, and that's why you're getting a wrong answer. And so the upshot here is that that's not the interior of the black hole that you would jump into after the measurement on R. And so, if you consider this, if you put the projector here, this was a check to show that you also get 1, but I'll skip it for time's sake. And let me now just go to conclusions. So I reviewed how the final state leads to this acausality for an infalling observer who chooses to do the amps measurements. And the new intuition that comes in from the gravity path integral, or rather, as I said differently, is that in the gravity path integral, it's baked in. Or rather, let me just say it's a result that B tilde is part of R. And so it gives you a set of rules that takes into account this fact that B tilde or the interior is actually part of R. And so it gives you these new rules. And if you modify the final state using these new rules, the acausality disappears. And again, it's taking into account that that you have a new interior. Well, let me just state this as a final punchline, that after the action of R, you generate a new interior with a new final state after acting on R. So let me stop there. Thank you.
Thank you so much for the very nice talk. So we have plenty of time for questions. You can either raise your hand or unmute yourself. Okay, Tadashi.
Thank you very much for very illuminating talk, very stimulating talk. And I want to know the property of singularity which you can expect from your analysis. So
from the gravitational path integral.
Yeah. From gravitational path integral, do we need to fine tune this effect of singularity? Is your final state, or is that quite universal property?
Okay, good. So let me say a few things. So first comment is that it seems that these results involving islands and wormholes and so on are insensitive to the singularity. Like the island is always far away from the singularity. Okay, so that's one comment. The other comment is that there's a connection which was discussed by Douglas Stanford in a talk at the KITP, that the results from the gravity path integral for computing the entropy are consistent with having a random final state. So like it's by consistent, it's almost like it's actually just equal to. What I mean is that, remember how I said that there's a small non-unitary term? Or when you compute, say, trace rho squared, and you go back. This thing, small non-unitary term. This thing, so if you have a random final state, your final state is a random state, then it's not perfectly a unitary. From suppose we consider the case where actually, let me say it that way. Yeah. So it's in my case, it's not a perfect isometry from B tilde to R. There's some small non-unitary pieces. This is a statement that if you have a random state on some collection of qubits, and you partition them into two equal sets, then you don't quite get a unitary from one half to the other. You need something a bit more fine-tuned, like these perfect tensors. Right? The perfect tensors would give you a state such that you get a unitary from one half to the other half, and so on. But yeah, so the gravity path integral looks consistent with having consistent with a random final state, at least from the perspective of computing something like entropy and so on. I hope that answered the question.
I see. So the result, only randomness is necessary to get a consistent result.
That's right.
Thank you very much.
We have a question from Emil.
Yeah, so it sounds like your answer to the question of what happens when you try to perform the AMPS check, that the person who's crossing the horizon trying to check the entanglement of B tilde and B ends up changing the black hole. The black hole that they find isn't the black hole that they thought they had. In other words, that what you're doing, sounds like what you're doing is you're changing the formation process of the black hole, because this this quantum that's crossing the horizon sort of to the past of where the AMPS measurement is being made, all of a sudden gets replaced with a different state. Yeah.
Mm-hmm.
So it sounds a little weird. It sounds like you say, okay, some measurement you can do in the future changes the black hole that I thought I had. So what's the status of setting initial conditions? It still looks very acausal, I guess, is what I'm scratching my head about.
Mm-hmm.
That you change the past of the formation process in the process of making a measurement in the future.
I mean, I share the same worries that this might lead to some other acausality. I mean, this is just it's a signature of the fact that the interior is somehow dual to or described by something which is space-like separated away from it. And I was not able to find any sort of contradiction, like some observable acausality that this implies, but would be interesting to search more. But I'm not convinced that there is a problem.
Okay.
I think that I guess I would view, say, your proposal, if you compare it to the Busso and Stanford, where you're saying, okay, instead of thinking of we're measuring here, instead of measuring at this system, we're measuring this other system. It's a bit like you effectively have a superluminal signal because of the teleportation, and so because of the final state projection, and so in some sense there's no consistent answer, because you will be in one reference frame one is coming first, in another reference frame another one is coming first, and so you will be you can argue one is happening before the other, but because there's a closed time-like curve, it doesn't, to my mind, make much sense to talk about that. I think I think you do get these causal paradoxes. We wrote a paper a while ago called "Do Black Holes Create Polyamory?" And I think also Seth Lloyd and John Preskill wrote a related paper before us, which effectively looked at these kind of causal paradoxes which you get because of the final state proposal. And I suspect there's no consistent way to fix it, because it's not unitary. You're making a final state projection, so you shouldn't expect this to be unitary, because when you have a pre-selection and a post-selection, that's not a unitary evolution. So how there's no way to make it unitary.
Well, I'm interested to revisit those paradoxes in light of this new interpretation. I think that might be a fruitful thing to do.
We have a question from Tokiro.
Thank you for the nice talk. And so my question is, even with or without final state projection, so does information come out to the outside? from the recent argument of islands and entanglement wedge reconstruction?
Does the information go outside? Well, let me see. Well, so the calculation of the page curve tells you that in some sense the information is outside, but it's very coarse. It doesn't tell you that it's not very explicit. From the discussion of the PETS map, it tells you that you can indeed learn about things in the interior of the black hole by doing measurements on the radiation.
Mm-hmm.
So the information is outside, but you can ask now, how much information can I see outside? Like, can I see all e to the s Bekenstein-Hawking? So far, we are not able to do that because these constructions rely on working in some small code subspace and so on.
Mm-hmm.
So the short answer again is, given the PETS map, it is a way of checking that at least some of the information inside the black hole does make it outside.
Mm-hmm. I see. So yeah, another question is, so in JT gravity model, so which part corresponds to the final state? You have end of the word brain as well as two insertion. I didn't understand it, but it's what the two insertion means. The purple and some wavy line.
Yeah, that's a good question. There's no explicit final state here. Well, I can say a few things. So, so one perspective is that there is no explicit final state in this model. Okay? It's just that the answers that you get from the gravitational path integral, say these pictures, is consistent with having a random final state. Okay, that's one perspective. Another perspective is to say that you have a closed universe, and there's this idea that a closed universe really has a one-dimensional Hilbert space. So even though it might seem that you're entangling this reference system with a closed universe, because the closed universe is secretly just one state, you're projecting on half of these. So here, you're projecting on these indices here. That's another rough perspective. Like this thing, this picture, if you ignore the closed universe, it looks like it's an entangled set of qubits. This dotted line can represent an entangled set of qubits, and then when you attach the closed universe on one of the indices, you've projected those onto some state. Mm-hmm. That's another perspective, but I don't have much to say about that.
Mm-hmm. Mm-hmm. So if we I'm maybe misunderstanding, but so does this closed universe Hilbert space give something like random phase, and do you interpret it as some random final state?
I'm saying that the answers that you get from implementing the gravitational path integral is consistent with replacing this the closed universe with a random state. Like a random state, I mean you put some state here psi and some state here psi, and then you consider the quantity you want to compute, say trace rho or trace rho squared, and then you integrate psi over the Haar measure.
So, do you mean the random state in one-dimensional Hilbert space of the closed universe?
Sorry, can you say that again?
So I assume that the closed universe has one-dimensional Hilbert space in some full quantum mechanical description, and I wonder, so yeah, I wonder, so where is this random state is in, on which Hilbert space, this random state?
It's not there. Like I don't know how to see it from the perspective of, like I don't know how to rewrite the closed universe. I really think it's just what I said, that I think I think for now we should just put aside this question of the dimensionality of the closed universe Hilbert space. Just put that aside for now. The only statement, the only definite statement I want to make is that the calculations from the gravitational path integral is consistent with having a with having a random final state. I think I want to leave it at that.
Okay, thank you.
Okay. If there are no more quick questions or comments, I think this is a good place to end. So we'll thank the speaker once again. And this concludes the evening session. So thank you everyone for coming. And yeah, I guess we still have one more day.
Thanks a lot.